let's get on with it. All right. Sure, all right, Kazi, then hand it when you can.
For this problem, how do you compensate for the overlaps?
Well, here we go. All right, so hello, Valeria. So let's go through this problem that we left unfinished from last lecture. How do I describe this situation? I have 16 times that I throw a coin, and how many times will I see HTTH on average? So I'm asking for the expected value, correct? So what I do is this. So what I will have is I will have indicator variables. That will do the following. So for K1 all the way to K equal to 13, the random variable will look at the next 4 entries. Do you understand? So first random variable x1 will look at the first entries of the word is made of 16 letters. So x1 looks at the first 4 letters. X2 will look at the 4 letters starting from 2 all the way. Why do I subtract 4 plus 1 here? Why do I do that? It's because beyond 13 you will not 13 and up you have 4 letters. Yes, if it's 14 and up we don't have enough. Understood? So that will indicate 1 if the k through k plus third tosses were of the desired pattern, h, t, t, h, and 0 otherwise. Now, what's the expected value of just one such random variable? The expected value of xk is, because if I just focus on any particular segment of the string, it's equally likely to be anything, right? It's equally likely to be any combination of h and t. So for this to be exactly the right combination of h and t would be 1/2 to the power of 4. You agree? 1/2 for the first entry on the letter that xk is looking at is h, the next is t, the next is t, the next is h. Each of them is 1/2. So I multiply 1/2 by itself 4 times, and I get 1/16. Now, how many words will I find? On average, it will be the expected value of the sum of the variables. Do you agree? x1 plus x2 plus x3 all the way to 13. And I calculated the expected value of xk because it's 1 times the probability I get 1, 0 times the probability that I get 0, that I get other patterns, right? So it's the expected value is the probability of getting that that string. And so I add them up and I get 13 divided by 16. In general, if I toss the coin n times, the result will be n minus 3 over 16 is how many on average will come up to be the pattern, right? So that means 13 16th is the average number that I will see the pattern HTTH if I throw it 16 times. Any questions before I move on?
So it's so you'll see it 13 times out of 16.
Yes, 13 times out of 16.
And
so
the one
exactly right. So if I simulate 16 games, right? On average, 13 of them will be containing. I will see 13 copies of HTTH. So there will be many examples like this for your exams that hopefully you will understand it. Good.
And is 1/16 basically the probability that you'll get HTTH?
Yes, somewhere in a particular place. You see
Okay.
why that's the expected value? Because it's 1 multiplied by the probability of getting 1, 0 multiplied by the corresponding probability of not getting it. But it doesn't matter. If I multiply by 0, I don't need to consider it. It's just 1 multiplied by the probability. So its expected value is the probability of seeing that from the cave place in the word onwards.
And this counts for the whole overlap part too.
Well, I don't have to worry about overlaps, because you see what happens is that the x1, if x1 is equal to 1, then x2 would be equal to 0, right? They are not independent, right? If x1 is equal to 1, it means I see HTTH, then x2 cannot be HTTH, because starting from the second letter, I'm not seeing the pattern. But so they are not independent. But doesn't matter, right? So basically, they will react. So I produce a random word having 16 letters out of H and T, and I then measure it using those variables by how many of I dissect it. You see, each separate random variable only looks at part of this word and checks whether or not that part contains the phrase HTTH. Good. And then moving on. That's what we spoke of last time. I hope you understood that discussion, guys. And now we talk about variance. Okay, so far you all understand what is a random variable and what's a function of a random variable. Please confirm that you do. Yes, so nothing needed. Yes, right now. So you understood what we did last time. Great. So now you see, knowing the average, it still doesn't tell us much about the distribution, because well, we can have the same expected value, and yet around the average, the things are very different from the average. You understand? So I don't know. I mean, in the morning I was watching some discussion about it, right? So there was not exactly averages. It was something about the power of language and language as a weapon, and it was in German. And naturally, their examples are very, they talk about right-wing parties, whatnot, which is not at all the focus that anybody should be paying attention to these days. They pay overdue attention to right-wing parties and not at all to left-wing parties. But that's a separate story. They spoke about prejudice and whatnot, right? And prejudice to me seems in a way like expected value, right? So you see, when I say phrases like, I say phrases like Russians are rude. Yes. What do I mean by that? If you go to Brighton, then it's more likely that somebody would say something rude to you than if you are going to maybe some other place. Good. So when it sounds like what I'm saying, take a typical average Russian, and that person is rude. So that's the expected value. What I imagine kind of like in a game. I imagine you have lots of figures, and they have all sorts of indicators, like in Diablo, it is stamina and all other things, if you remember that game, right? So all sorts of indicators, then you average per indicator, and that's how you create what you call the average person, right? They take a population, any population, and the average person of that population will be fix certain parameters, provided there is some way to measure those parameters. You can just average them out, quantify and measure, right? So how strong is the person? Maybe how much weight can they lift? That would be something that you possibly can quantize, right? And then you can average those quantities. Does it make sense? Yes, guys, are you following me into the dangerous waters that I'm leading it into? Yes. And so then the thing, when I calculate this, let's say this supposed average person. So for example, how good are people in a particular class in math? Let's say I calculated the average and it's 50. And what does it take? Does it say that they are all like this 50? They all look like a 50 score student, or do they look something entirely different? Maybe many people scored 0, half of them scored 0, half of them are 100. You see, it's a different picture. Does it make sense what I'm talking about, guys? Right? So we are now trying to gauge another parameter to see how true to actual individuals that we see is that average individual that we calculated. And so here we have W could be 0 with probability 1. In other words, the random variable is actually the same as the average, right? The average person here is this. Now I might have scores of the form 1 and -1, each with probability 1/2. So you can see that the average is somewhat different from any of them, right? So 0 is in between, -1 is somewhat less than 0, 1 is somewhat more than 0, right? But they are a little bit closer than maybe Z, which is -100 and +100, if of course scale means anything, right? So you see, let's say maybe this represents different populations, and you might say on average 0, nobody is violent, right? No, those populations have the same average, the same quantity of violence. Here, though, you just whatever you meet is completely harmless. Here you meet a person that is somewhat not pleasant and somewhat pleasant. Here you meet people that are extremely pleasant, like bipolar, right? Extremely pleasant or extremely unpleasant, right? And on average, I suppose, I'm not sure if that's a good. On average, you see. But you see, you would not have the same kind of experience. You go to this country, you will just feel, oh, everybody is kind of average. They are not particularly unpleasant, particularly pleasant. Here, you don't actually see the average person. You see somebody that is slightly unpleasant and someone that is slightly pleasant, right? And here, it's like a little bit like French experience, right? You go there and they are extremely unpleasant, or, well, that's not true about French, but extremely pleasant. Good? You understand what I mean? So it's an entirely different population. So how do we improve our understanding of how close to the average are the individuals? So that we talk about the variance. In other words, the expected difference, on average, how different will be an individual from that average individual that I calculated. Yes? So if mu is the average individual for this quantity, then we might want to try to calculate the expected value of absolute value of x minus mu, right? X minus mu is, x is the actual observation that I have, and mu is the average. How different are they? And in absolute value, I do it, right? But the thing is, absolute value makes it a bit difficult to carry calculations. You understand? So absolute value is not, it's a piecewise function. It's not that terribly nice. And for other purposes, as you will see, other theorems, it's much nicer to deal with squares. Understand? Square is a differentiable function to begin with. All sorts of various reasons that you will see. So instead we will define the expected value of x minus mu squared. Okay, because you can see that the square will, again, if there is a big difference between x and mu, then the square will emphasize it, right? So it's a sort of measurement of the difference. And we will use this as a sort of measurement for how similar is a typical individual to the average individual that I calculated here. Yes? So here it is. It's called variance. Variance of x is the expected value of x minus mu squared. Okay? And so I can carry out the following calculation. So variance of x is the expected value of x minus mu squared. If I square, I get x squared minus 2 mu x plus mu squared. And now you remember, this is a function, right? And I can use the original distribution of x to calculate this expected value. I don't need to switch to the new process. So I have, it's the summation over the probabilities that are positive for x's for which the probabilities are positive. Here we have it. And I can distribute the probabilities, and I see it's the x squared probability x minus 2 mu x times px plus mu squared the probability here. So what do we get here? First guy is the expected value of x squared. Yes, that's the expected value of x squared. Agreed? Next is it's minus 2 mu times the expected value of x. Here it is. And the last thing is just mu squared. The sums of the probabilities must equal to 1. Everybody understand? So what we have is the expected value of x squared minus 2 mu squared plus mu squared, which is the same as simply the expected value of x squared minus the square of the expected value. Are you with me? Everything that I said so far made sense, right? So you understand what we're trying to gauge, right? And I mean, you might, of course, not be happy about the square. Why square? Since the exact thing that seems to be measuring is here we found the average, and here we observe some random individual. And then the expected value of the absolute value of the random individual minus the average will give you a sense in how much the random individual is different from the average individual that you calculated. Yes? So the average Russian in my example is rude, but maybe you will find Russians that are very, very wonderfully pleasant, and they will be offset by Russians that are wonderfully unpleasant. And therefore, on average, it's somewhere, it hovers in the rudeness, right? But your experience is hot and cold, right? It's like, it's not uniform temperature. Right? That's why average is not good enough. It might be very separated, very hot, very cold, or it might be mixed, and you will have a very different reaction to it. It's like you can drink mixed cold water and hot water, or drink scalding water and freezing water. That's a different feeling, I imagine. Yes. So the variance is a way to gauge it. So let's calculate the variance of tossing a fair die. So we already calculated the expected value of a fair die. That's the summation k over 6, where k is 1 to 6, and that's 7 over 2. So we know the average. On average, a fair die will land on the number 7 over 2. And you understand how I imagine this, right? We have this table. First die landed on 5, next die on 1, right? And if I average those numbers, and I had many, many tosses of the die, I will find that the average is 7 over 2. Good. And then what's the variance? The variance, I need to calculate the expected value of x squared. Okay, and what's the expected value of the square? That's simply k squared times 1 over 6. You all understand that, guys? Because I can use the same probabilities in the same sample space, but I'm just having k squared here. And the summation of k squared, do you remember what it is, guys? How do you sum k squared? It's gonna be 6 times 7 times 13 over 6 times 1 over 6. Do you need a refresher on summing squares? Yes? All right, let's do a refresher. I muted my microphone accidentally. You can see my board, yes? So here is the idea, guys, right? So if I have, I think about it, how do I add up 1 plus 2 squared plus 3 squared plus n squared? Yes, so we can tell ourselves, we can do it using calc 1 methods, but we can also tell ourselves a story since we are in combinatorial analysis. What is it talking about? I think it means that here me, right? Can you guess what's my age? Not quite, right? You don't know exactly how old I am. And I have 2 brothers. It's not true. I don't have 2 brothers, but you cannot guess how old am I. So maybe I am, n could be 100, right? I'm between 2 years and 100 years old or something, right? So 101 or not, right? And my brothers are younger than me. Yes? 2 brothers are younger than me. So what are the possibilities for our combined ages? For our combined ages, it could be that we are all of different ages, right? So we have n plus 1. It should be equal to n plus 1, choose 3, where n plus 1 are all the possible ages for me and my two brothers. You understand what I'm saying, guys? So I'm thinking that I am older than my two brothers. I'm the eldest of the three brothers. And my age is either 2 or 3 or all the way to n plus 1. Good? So, and the first line is counting what? The first line is counting, well, both my brothers I am 2 years old and my brothers are each 1 year old, or I am 3 years old and my brothers are either 1 or 2 each of them. So each brother has 2 years as possibility, right? So brother 1, brother 2, brother 3, right? We just have to be careful, right? So n plus 1, and how do we do that, right? So I have brother 1, brother 2, and I'm 3, right? So those are we are all different ages, and then I am the oldest, and my two brothers, I'm not sure which of them are the oldest, so I think it should be multiplied by 2. You agree? And then plus. Now we consider the possibility that well, I am the oldest and both brothers are of the same age, right? So here they were of different age, and now the other possibility, they are of the same age. So then I have to take n plus 1, choose 2. Good. And let's see what we obtain. So that would be n plus 1 times n minus 1 divided by 3 factorial, which is 6, multiplied by 2. It's multiplied by 2. It is well, I'll write here the 6 and multiply this by 2 plus here I have n plus 1 times n divided by, it's divided by 2, but I'll divide it by 6, so I'll multiply it by 3, and I have a 6 here. Good. So they are of the same denominator. Good. So then I can factor it out. You follow my explanation, guys? Yes. Make sure that I'm not making some error. So I factor it out. I have n plus 1 n that I factor out, and n plus 1 times n that I factor out, and I have that 2n. So I have basically 2n minus 2 plus 3 multiplied by n plus 1 and by n divided by 6. Altogether, I get 2n plus 1. So if I arrange it in order, I can say it is 2n plus 1 times n plus 1 times n divided by 6. That's my formula. Good. So that's how I obtain this. Okay, so what is this 6? 6 is n. This is n plus 1, it's 7. 6 times 2 is 12, plus 1 is 13. So yes, the formula that I wrote was correct. It agrees with what I said here. Good. So then the variance will be the expected value of x squared. Expected value of x squared minus the square of the variance. So I take 91 over 6 minus 7 over 2 squared, and I get 35 over 12. So now let's consider a useful observation. So variance of ax plus b is simply a squared multiplied by the variance. Shifting does not change anything as we would have expected, right? Why shouldn't it change anything? Because you are measuring not where the individuals are located, but where the individuals are located in reference to the average. So adding b, you're just shifting everything to the right or left by b units. And what matters is just the scaling times a. So here is a proof of it. Let mu equal to the expected value of x, then the expected value of ax plus b is, according to the linearity, a expected value of x plus b. So it's equal to a mu plus b. So again, guys, as I'm speaking, I hope I make sense. It's not always clear to me if I do. Would you confirm you understood so far everything? Yeah. Thank you. So then we have a variance of ax plus b is the expected value of ax plus b minus it's basically ax plus b minus this new average. So then what do I see? I see that b's are gone, and I see ax minus am and all of it squared. So I can factor out a squared out, and it's basically a squared times the expected value of x minus mu squared, which is exactly as I expected. Clear? You see, because expected value is linear, so I can factor out any scalar, right? So the a squared, it is here. I factor it out to the parentheses, it's a squared, and then it pops out from the expected value. And the expected value of x minus mu squared is simply the variance. Wonderful, let's move on. So now we talk about properties of variance. So we have seen that the expected value is always the sum of the expected value of a sum is always the sum of the expected values. And that's true in any circumstance. It is important to know whether this will be also true of variance. So we need the following idea. So we have covariance that we're talking about, okay? So covariance is defined as the expected value of x minus its average times y minus its average. And you can see that in the case where x and y are the same, that simply becomes variance. So covariance is just a generalization of variance. Good? Now, let's observe what we obtain when we calculate the expected value of covariance. So first I can multiply things out. Here they are multiplied out. So I see it's the expected value of the product x times y minus, minus the average of x times the expected value of y minus mu y expected value of x plus mu x mu y. And when I simplify it, here it is simplified, I get that it's the expected value of x times y minus the expected value of x times the expected value of y. Here is our formula for covariance. Some simple properties. So property A. Naturally, if I switch x and y, covariance of xy is the same as covariance yx, because look at it, it's the expected value of the same product. As mentioned, covariance of x with itself is variance. And then you have this scalar multiplicativity. Covariance of axy, I can factor out the a. And covariance of x1 plus x2y ends up being covariance of x1y plus covariance x2y. So it behaves, in each coordinate, it behaves like a linear function. If you took linear algebra, you realize that you're dealing with a multilinear map. So here I prove, actually, I even bother proving A, right? Covariance of xy is the expected value of xy minus expected value x, expected value of y, which obviously is the same as expected value yx minus expected value y, expected value x, which is covariance yx. A bunch of them are obvious. Anything here not obvious may be D. Yes, guys? D is the only thing that I think is not immediate. Maybe very, very close to immediate, but maybe you doubt it's true. It's right away obviously true. Am I right? So D means covariance of x1 plus x2y. It's the expected value by according to what we just derived above. It's the expected value of the first term multiplied by y minus the product of the separate expected values. So this part I can write as the expected value of is additive, right? So I can write it as the expected value x1y plus expected value x2y minus, here I can expand this part, so it's minus this product, which when I distribute, you observe that the red part is the expected value of x1y, the blue part is the variance, sorry, of x2y. So you can see the reds form covariance x1y, blue form covariance x2y. And that means in general, look at it in general, what I can do is covariance of a sum in one coordinate is pretty much the sum of covariances where I fix the xk. So far, everything clear? Now, I can obviously observe the following. So then covariance of some summation against another summation, it will behave like multiplication. It will be, because I can first expand all the x's, then I can expand all the y's. It will be all possible sums of covariance of any y against any x, any xk against any yj. That's what the summation means. You understand? So if I expand it, I expand first the x, you have all the y's against x1, all the y's against x2, all the y's against x3, so on, right? And then I expand the y's. In the second coordinate, it's also linear, obviously, because I can interchange, right? So it follows immediately. So it's linear, and then the result is that covariance behaves just like multiplication does. It's just like I have, when I have that, I will have to add covariance of any xk against any yj. That's what the summation is saying. Good? You see it? Wonderful. So now we have variance of a sum. What is a variance of a sum? Variance of a sum now is covariance of the same sum against itself. Agreed? Variance of summation is, remember, covariance is just a generalization of variance. It's just I'm using for covariance, I'll have to use x minus mu times x minus mu. I'll have to use the same variable here. Good? So this is then the corollary, is that variance of the summation is going to be, when I expand it, it's going to be covariance of each individual. I feel like I'm losing you, so I'll actually give you a quick calculation here so you understand what I mean, right? So suppose that I have variance of only two. Right? So we have variance of x1 plus x2. Now that's the same thing as covariance x1 plus x2. x1 plus x2. Yes? And that means I have every combination. So I will have covariance of x1 against x1, of x1 against x2, of x2 against x1, and of x2 against x2. Do you all see that? Yes? Now I can group some of them, right? So if I see the same letter here, so for example, what is this guy and what is this guy? I can separate them together, and I see that this is variance of x1 plus variance of x2. And then I have the blue regions, here they are. They are the same because it's 1 against 2. It's x1 against x2 in both situations, and the covariance is symmetric, so I can simply write plus 2 covariance x1 x2. Understood? That's what I and I can do that in general. So let's think what happens if I have n sums, variance of n sums. Then what you would observe is that you would have exactly one meeting of one variable against itself, right? For each 1, 2, 3, all the way to n. Good. So what you have is this situation. Okay. What you have is that variance of n of them, I can group together the encounter of each xk against itself. So it will be the sum of the variances, but plus what? Plus all the other combinations, all the other meetings, right? So where xk meets against xj. Good. Actually, how many meetings will you have? How many terms are in this sum? Could you please tell me? How many terms are in the summation, if you understand it? So we know there are n terms in the first sum. We have variance of x1 plus variance of x2 plus variance of x3, and so on. How many terms will we have in the summation still involving covariance? No, not n squared. Kafka protocols, easy, right? What is happening here? Intuitively, each xk meets against each xj. So we have left xk's and we have right xk's. No, Naomi?
Will we just have n?
No. No. Shotaro, of course, you were close enough, right? But it's not n squared.
Isn't n squared minus 1 because j can't be k?
Not minus 1.
Plus 1?
No. Come on, you already finished exam 1 and that's it. You don't need it anymore. Not to mention the rest of you, right? I wish I could. Yeah, I don't want to displace my frustration because you came, but those that didn't. Yes. Yes, Murshika, good. N squared minus n. Or here is how we figure it out. Look at it, guys. So what do we have? We have variance of x1 plus xn, right? This I can write as covariance of what? Covariance of, let me color the first bunch as x1, the reds against the blues. x1 plus xn, and the blues are x1 plus xn. Good. So what happens here, right? So each will encounter, each red will encounter each blue. You agree? Each red will encounter each blue. You will soon understand it far better. So give it a little bit of time. So what happens here? So first I can group together all the encounters where like meets like, where red 1 meets blue 1, when red 2 meets blue 2, right? So that would be all of them variance. It will be covariance x1 x1, covariance x2 x2, right? So I group it like this. I can write it as k equal 1 to n of variance of xk, right? Plus the other encounters are where I can write it like this, for example, right? Where k does not equal to j, covariance red xk against blue xj. You are with me? So those are encounters. So I broke it up into two types of encounters: encounters of like against like, and encounters that are heterogeneous. Yes. So the heterogeneous, how many heterogeneous encounters do we have? How many terms are we going to add if k is not equal to j? Well, very simply, you need to choose two, right? So how many do we have? We need to choose two letters. N choose 2 multiplied by 2. Why by 2? Because you see, when I choose them, when I say n choose 2, I say place smaller here, larger there. Let's say, right? N choose 2 means order them from smallest to largest. When I multiply by 2, it could be that the larger is here, the smaller is here, right? So it is simply, so the summation is over n choose 2 multiplied by 2, which is simply n times n minus 1. And Murshika said it's n squared minus n. Same thing. Make sense? Guys, you understand, right? So right, so there is going to be some variance, but there is all this covariance stuff happening still. So we don't expect that the variance of the sum is sum of variances in general. Good. We don't expect, it is, we notice, we observe that the expected value of a sum is the sum of the expected values, regardless if the variables are independent or not, doesn't matter. Good. And here I gave you a few examples of how that looks. Okay. And here is an important theorem. If x and y are independent random variables, then covariance of x and y is 0. So covariance is something that you use for measuring correlation, by the way, but I'm not going to go into that. Okay, covariance is part of your formula in measuring correlation. So independent means there is no correlation. So covariance of x, y equals 0 is if x and y are independent. Now, how do I know that? Okay, so covariance, you understood the calculation. By pure calculation, covariance xy is the expected value of x times y minus the product of the expected values, yes? Now, what is the expected value of x times y? It's every possible x in here against every possible y in here, right? It's xi times yj, and I sum over the probability that x equals to xi and y equals to yj. Because what are the values that xy can take? I can work with my original sample space, right? And I just say, okay, how do I get, what values can I get? Some value of x times some value of y. Do you understand this formula? Xi times yj, guys. Look at it and confirm that you understand, or do I need to speak more about it? That the expected value of x times y will be will look like the summation. Do I need to say more? Naomi gives me the impression that I do. Do I? Okay, then let's understand what is x times y. So we have a sample space. And the outcomes of the sample space are S1, S2, S3, S4, right? Etc. Right? So some of those, so when I have a random variable x, so each of them, let's say this has some probability, right? This has some probability. This has some probability, right? So it's P_S1, P_S2, P_S3, P_S4. Now they add up to 1, of course, if that's also the possibilities. Now imagine that I first when I apply x labels them as, let's say this is labeled as x1, this is labeled as x1, yes, and then maybe this is labeled as x2, and this is labeled as x3. Okay, let's say we have that labeling, yes, and then I run the variable y, and the random variable y will create different labels, right? So maybe it will say that this is y1, and this is also y1, and this is also y1, and this is y2. Good. So we have different labelings, yes. So when I ask myself what is the expected value, the expected value of the product of x times y, what am I asking? I mean, you see, I can consider, you see, so I run the experiment, and I multiply, once I get a result, I multiply the x's and the y's together. That's what happens, yeah? So that would be, in this particular case, I can write it as x1 multiplied by y1 times the probability of S1, right? Plus maybe I get so x1 times, I can write here x1 times y2 probability S3 and so on, right? That would be, you know, and so on. Make sense? I can go through the sample space. What happens if this outcome came about? That would be y1 times x1. This outcome came about, it would be y1 times x2. This y1 times x3, right? And I have all the combinations. Now, when I don't have this picture, what can I imagine in general happening? I just imagine all the possible values of x multiplied by all the possible values of y times the probability where that it happens. That x equals to at the same time to something and to something else. In this case, many of them will be 0. Many of the probabilities will be 0. Do you understand what I mean? So I could have calculated this as follows. I can say so the expected value of x times y, it's it's let's say x1 times y1 times the probability that x1 equal to, so times the probability that x equals to x1. And y equals to y1. What is that probability? What is that probability? Well, I look in the previous picture. Look at it. X equals to x1 and y equal to y1. When does it happen? We have x1, y1, and that's it. Right? We don't have anything else. So that's just probability S1. Agreed? So that would be times probability plus, next I will consider x1 matched with y2. I considered all the x1 matched with y1, and then I have x1 matched with y2. That's a possible result. You agree? Maybe y generated y2, x generated x1. Good. So that would be this times the probability of x equal to x1, y equal to y2. And what is this? X1, Y2. So let's say we have X1, Y2. We have it's probability of S4. Agree? There is only one instance. X1, Y2. It's S4. Yes, I'm not missing anything. Good. So that thing is simply probability of S4. This was the probability of S1. Good. And then I continue. Now I have, do I have Y? I didn't say Y3, right? So that's it. There is only Y1, Y2. Yes. Now I upgrade. Maybe it's now X2, Y1, right? So then I ask, what's the probability? So X2, Y1, X2, Y1. Probability of generating x2 and y1. I write a shorter version. I don't want to say x equal to x2, y equal to y1, right? So what is that? Let's look over there. Do I have x2, y1? x2, y1, it's s4, yes? Nothing else, right? x2, y1, it's...
Isn't it S2?
S2, right? S2. Yes, so let's see. Yeah. And then we have x2, y2. Note it, x2, y2 doesn't exist, yes? So plus x2, y2. And that would end up being 0. Good. And then we have what? I think I have x3, right? So there is an x3 there. Yes, and then we have x3 and y1. x3, y1, probability of x3, y1. That is probability of S1, right? And the rest will be 0. So there is also
S3.
Huh?
I think it's S3.
S3. Okay, S3 then. The point is, you see, you consider all possible combinations and multiple. You see why? Because those are obviously the possible results that could have occurred, right? If I have x times y, everything that x could generate times everything that y could generate could potentially occur. Sometimes it doesn't, as in this case, some of them are 0, right? But you can consider all the combined possibilities, and then that would be your expected value. Do you agree? Because what do you do? X times y is just a particular score. The score could have been formed as some score of x multiplied by some score of y. So I considered all possible scores here. There is also x3, y2, but it doesn't occur. I can write it more, you see? So there is x3, y2, but it also has probability 0. So those that don't occur will be multiplied by 0. Good? You're with me now? It's really, there's nothing so difficult here, yes? It's just arithmetic. Now, if x and y are independent, what is this? This is intersection, right? X is equal to xi and y equals to yj. Do you remember that independence means that that the probability of intersection of two events is the product of the probabilities? You remember that? No, you forgot? Do I need to? So let me remind you if you forgot that as well. So when I say event E and F are independent, right? What do I say? I say that probability of E given F is not changing the probability. It's the probability of E. Yes. And what does and this by definition is simply probability EF divided by probability F. So that means that probability EF should equal to probability of E multiplied by probability F. Yes, that's independence. So you understand all those formulas. Good. So if it's independent, I can say it's simply the probability of x equal to xi times the probability y equals to yj. And what do I have here? Now it becomes just you see, look at it. I see it's really xi probability of x equal to xi times yj probability yj, and it's every guy against every guy, which is just exactly what happens when I multiply parentheses. You understand? So I factor it out, and I see this is what? This is the expected value of x, and this is the expected value of y. Do you understand? That's a very important step. Multiplication. Right? When it's separated, I can now group together the x's and the y's, and that's really the x group multiplied by the y group. Every possible x group multiplied by every possible y group. And then that's the same thing as I can factor it out. It's multiplication. Confirm if you understand, or do I need to say more? It's a very important part here. It's basic algebra, but very important basic algebra. All right, one person confirmed, the rest. And you, Abhishek, do I need to elaborate? Great. So understood, yes? Everyone understood how it works. It's multiplication. It just you uncouple it. It's what do you call it? Unfoiling or whatnot. So again, guys, don't be pressured by anything. If something is not understood, I will try to explain. Just be sure that when you say yes, it's a sincere yes from your heart. Yes? So let's now, so here is the consequence, guys. Look at it. The expected value of x times y, it's the product of the expected values, but covariance is this expression. So it cancels identically to 0. So if the random variables are independent, covariances will be 0. Good? So what's the consequence? The consequence is that in the event that x's are independent, variance of a sum is the sum of the variances, because the covariances of each xk times xj will disappear and be 0. Make sense? So in the event of no correlation, we are not going to talk about correlation, but yes, so then you would have variance of the sum is sum of variances. That's very important. That's why we are, so this definition, it's going to be part of all sorts of laws, like the law of large numbers, which we will talk about soon. Good. Here is an example. So there are 5 fair coins. One coin is picked at random and tossed. Let x be the number of fair the number of the fair coin, right? In other words, what it displays, I suppose, coin 1, coin 2, right? and y be 0 if tails and 1 if heads. Calculate the following values. Calculate the expected value of x and the expected value of y, and then calculate the variances and whatnot. So let's be sure that we understand the question, right? So what we have here is the coins are labeled as coin 1, coin 2, coin 3, coin 5, right? All the way to coin 5. And we pick a coin at random. So first X is representing the coin that is picked at random, right? And Y represents, regardless of what coin picked, it represents after we toss it, whether we get tails or heads. It's 1 if heads. Good? So I want to know what's the expected value of X and what's the expected value of Y. Okay, you say for X it's 3. And expected value of Y is 1/2. Yeah. All right. Let's get on with it, right? So for the first part, we randomly pick one of 5 coins. So the probability that coin 1 is picked is 1/5. Same for all the others. And what we're averaging is 1 plus 2 plus 3 plus 4 plus 5. And multiply that by 5, by 1/5, right? And multiply it by 1/5. So the result is obviously 3. For the second part, how do I calculate the expected value of y? I can always reduce to the universe where I pick coin number 1. Do you agree? Because whenever I toss something, it's the same result as if I were tossing coin number 1. And that means that the expected value of y is 1/2. As Naomi said, and maybe a few others, but I'm not sure if the others said it. No, they did not. Yes, only Naomi said. Okay, good. 3 and 1/2. Good. Now let's calculate the variances. Variance x, variance y. So I need the expected value of x squared. I sum up k squared times 1/5 and I get 11. Yes. And then variance is apparently 2. Variance of x is 2. The expected value of y squared also is 1/2. You agree? Because it's 0 squared times 1/2 plus 1 squared times 1/2. So it's 1/2. So the variance of y is simply 1/2 minus the expected value squared, which is 1/4. And now let's consider what is the covariance, right? So I did it on purpose. I carried out all the possible combinations, you see? To give you an example, I carried all the possible combinations. But what do you think the answer will be? If I carry out all this long calculation, what will it be? Covariance between x and y. In other words, the you see, covariance it represents roughly, so you have to understand correlation. You see how what would the result on X affect the result in 1? Exactly. So the actual calculation, if I carried it, it's 1. You see, so it's this. It's whatever I wrote over here. It's all combinations of what X could have generated. X can generate number 1 through 5, and Y can generate either 0 or 1. Yes. So I carry out basically there are 10 entries here, right? 5 multiplied by 2, 10 entries. And when I calculate all those 10 entries for 10 entries for the expected value of X times Y minus the expected value of X times expected value of Y, that's the last number. 3 times 1/2 is the expected value of X times expected value of Y. I get 0. Good. And then in particular, what's variance of X plus Y? Variance of X plus Y will be the variance of X plus variance of Y, which is 2 plus 1/4 or 9/4. You understood the idea, guys? Because the outcome on the coin is independent from the coin that I pick. Because it's a fair coin, right? Each of them behaves the same way as the other coin. It will not affect the probability. Good? 2 fair dice are rolled. Compute the expected value and variance of the sum on the dice. Go ahead, please do it. That's our last question for today, quickly. Sum on the dice, right? Variance, expected value, and variance on sum of 2 fair dice. Come on, guys. All right, so let's do it. I don't know. So expected value of each is 7/2. And therefore, the sum of the expected values is 7. Yes, so the sum on the dice on average will be 7. Do you agree? I hope you see that intuitively, by the way, right? You see why the expected value should be that. So then we look at the expected value of x squared, and of y squared is 91/6. Variance, if you calculate, is just expected value of the square minus the square of the expected value. So it's 35/12. And because the dice are independent, the sum of the variance is simply 35/12 plus 35/12, or 35/6. It's going to be the variance. Yes? You want one more question or not anymore? You want to go? All right, so then let's call it a day. Goodbye. Have a good one, Murishika.